Swayam Prabha. Digital India. Educated India.
Welcome to the second lesson of the fifth module, which is on bending of beams part 2. In fact, in the last lesson of this particular module, we have discussed some aspects of the bending of beams. We have introduced what is meant by beam, and then we have introduced the concept of shear force and bending moment. Now, in this particular lesson, we are going to look into the relationship of shear force and bending moment with the different types of loadings as we will go along. Well, then once this particular lesson is completed, if someone goes through this particular lesson, one should be able to understand the relationship between different types of loads and the stress resultants, which are shear force and bending moment. And if you remember, last time we had introduced and we had discussed the aspects of shear force and bending moment, and these quantities we call as stress resultants. Also, one should be able to evaluate reactive forces, the shear force and bending moment at any point in the beam for different kinds of loading, or in the length of the beam at any section we will be in a position to evaluate the shear force and the bending moment once we go through this particular lesson. Now, the scope of this particular lesson includes recapitulation of previous lesson. Now, establishment of the relationship between loads, and when we mean loads, the different kinds of loads, it could be uniformly distributed load, it could be concentrated load, or it could be concentrated moment, and the relationship of these loads with shear force and bending moment, and thereby we will look into various aspects of it. And this lesson includes examples for evaluation of reactive forces, shear force and bending moment for different beams under different loading conditions. So, this is the scope of this particular lesson. Now, let us look into the answers of the questions which were posed last time. Now, what is the difference between a bar and a beam? Now, in the last lesson we have discussed the concept of beam, and if you remember, as we said, that when a member is subjected to loads in its transverse direction, which is perpendicular to the axis of the member, we have designated those members as the beam. So, members subjected to loads transverse to the axis and are termed as beam, and the members are subjected to forces or moments having their vectors perpendicular to the axis of the member. And this is what is different from the bars. Bars are subjected to forces or moments having their vectors along the axis of the member. Now, if you remember that when we discussed about the axially loaded members, in which if this is the member and this is the member axis, then the force was acting in the direction of along the axis of the member, and this we have called as the axial force. Consequently, we have seen that if a bar is subjected to a twisting moment which is about the axis perpendicular to the cross section of the bar is the twisting moment, and then the direction of this vector direction of this twisting moment is along the axis of this bar. Whereas, in case of members which are designated as beams, there the loads are acting in the transverse direction which is perpendicular to the axis of the member. Also, if we look into the moments which can act about these two axes, if the moment acts about this particular axis, which is in the plane of the cross section, the vectorial direction, if the moment acts about this particular axis, the vectorial direction is perpendicular to the axis of the bar. Again, if the moment acts about the vertical axis, then also the vectorial notation of this particular moment is perpendicular to the axis of the bar. So, the member which is subjected to the loads or the moments, the vectorial notation of which is perpendicular to the axis of the bar, normally we designate those as beams. So, this is the difference between the bar and the beam. Now, what are the different types of supports that are used in beams? Now, this aspect we had looked last time. We had looked into the aspects of supports like pinned support, or we have called that as hinge support, the roller support and the fixed support. These are the kinds of supports that we encounter in beam members. Now, these are the types of beams which we have discussed. The first one is of pinned category or hinged category, and in a diagrammatic notation we generally indicate this kind of diagram. This is the roller support where the horizontal movement is allowed, and this is a fixed support where no movements like horizontal movement, vertical movement or the rotation, anything is allowed. Here the vertical movement and the horizontal movement is restricted, but the rotation is allowed. Here the horizontal movement is allowed, the vertical movement is restricted and the rotation also is allowed, and here all three quantities are restricted. Now, if we look into the part of this hinge type of connection, here if you look into, you see that when this is a part of the beam, when it is loaded, it is undergoing rotation. If we call this is the axis of the bar, then with reference to this original axis it is undergoing rotation, whereas this particular point which was originally at this position remains here. That means no horizontal or vertical movement is allowed, but the rotation is allowed. So, this is hinge type of connections or support. If we look into a support which is a roller kind of a support, where under the action of the load, as you can see, it moves in the horizontal direction, it cannot move in the vertical direction, but it can have the rotation as well. Please note over here, it moves in the horizontal direction as well as it has the rotation. Now, here if you look into that, with respect to the original position of the beam, it is having rotation in its from original position, it has moved. So, in the horizontal direction it has movement, if we call this as delta horizontal, we have rotation theta, but the vertical movement is restricted for the roller joint. So, if you note it over here, you see that we have movement in the horizontal direction as well as the rotation. Well, so these are the different kinds of supports that we encounter, and the last question which we had was, what is the sign convention for shear force, bending moment and axial force? Now, this aspect we have discussed last time, that normally for the shear force and bending moment, when we compute at any cross section of the beam, we must plot these shear force and bending moment with proper sign or place them with an appropriate sign, and this sign convention can be of different types. Now, the sign conventions which we will be following over here based on the initial sign conventions as we have looked into in the stress diagram. Let us look into that aspect. Now, here if you remember that when we dealt with the stresses, there we on an element, if we look into a two dimensional element of a rectangular configuration or a square configuration. Now, here the stress resultant acts in the positive x direction, and that we have called as positive. Now, here the shear which is positive is a positive y direction, and on this phase, so this we have called as a positive phase, where axial force is positive in the positive x direction, shear force is positive in the positive y direction. Now, on the negative phase, the axial force is acting towards the negative x direction and the shear force is acting in the negative y direction. So, in to keep a parity with this, here the convention which we have used is the shear force on this right hand side. Supposing this is a part of the beam, if we call del dx is the length which is taken out from a beam of length dx. Now, on this the shear force which is on the right face is acting upwards, moment which is anti-clockwise, they are positive, and axial force which is directed towards the x direction, they are positive, and the reverse are acting on the left hand support. So, these are the positive convention, and reverse of that is the negative convention. So, these are the sign convention which we will be following, in fact right through the discussions as we will go along for different lessons and modules. We will go by these particular conventions, and this convention in fact we have used in the evaluation of the stresses in at a point when we have discussed with respect to the axial stress. Well, now that as I have told you last time that the basic objective of this kind of analysis on beams, when a beam is subjected to the transverse loads, finally we like to evaluate that what is the stress this particular member is undergoing because of such loading, and what is the deformation in the member. Now, to know precisely that what is the stress level at any point and along the length of the beam, we need to know how these two quantities, the stress resultant, the shear force, the axial force and the bending moment, how they are varying at a different cross section along the length of the beam based on the loadings it is subjected to. Now, to do that, let us look into some of the aspects of that, how different kinds of loads can be related with the stress resultant quantities, which are nothing but the shear force and the bending moment. Now, if we consider a small segment of the beam, let us say that we have a beam over here which is supported at this particular end, and we like to take a small segment out of it which is of length dx. So, this particular segment is drawn over here. Now, this particular segment on its sides are given the positive shear force and the positive bending moment. Here it is in the opposite direction. Now, if we, and also it is subjected to uniformly distributed load of intensity q per unit length. Now, if we write down the equilibrium of the vertical forces, then we get that V plus dV, which is acting upwards in the positive direction, V plus dV minus the force which is acting on the left hand side which is downwards, which is negative V. Q is the load per unit length. So, over the length dx, it will be q times dx, is again acting downwards, which is negative. So, this is equals to 0. Now, this particular expression gives us that dV dx is equals to q. Now, the meaning of this particular expression is that slope of the shear force is equals to the load q. Now, if you look into this particular expression, that if this particular term q is equals to 0, then dV dx equals to 0, and if dV dx equals to 0, then the shear force gives us a constant value. So, wherever in a beam, if we do not have any load, then if we like to compute shear force in over that particular portion, then the shear force will be constant over that region where there is no load. So, this is what is being interpreted from this equation, that if dV dx is equals to 0, then the shear force is constant in that particular portion of the beam. Now, if the q is uniformly distributed over the length of the beam or a portion of the beam which we are considering, then dV dx also is equals to q, which is constant. Now, if we integrate it, then we get V, which is varying linearly over that particular portion. So, if we have q which is constant or uniform over the portion, then dV dx is constant, and consequently the shear force will be varying linearly in that part of the beam. So, this is what we get from this particular diagram. Now, supposing if we take the moment of all these forces with respect to this left edge, then what we get? If we take the moment of all the forces with respect to the left edge of the beam, then we have this m plus dm, which is in an anticlockwise direction, if we consider that as positive. Then on the right hand side we have v plus dv times the distance dx is the moment. So, b plus dv dx, which is also causing anticlockwise moment, which is positive, minus on the left hand side we have clockwise moment, which is minus m, and the load q over the length dx is causing again a clockwise moment with respect to the left face, which is q times dx is the total load times half the distance, which is dx by 2. So, this gives us the moment equilibrium, and if we eliminate the terms which is the product of the small quantities dv dx q dx square by 2 kind of a thing, then we have this m gets cancelled. So, here we are left with dm plus v times dx. So, this is equals to 0, rest of the terms gets cancelled out. Now, from this we get that dm dx is equals to minus v. Now, this expression tells us that the rate of change of the moment is equals to the negative of the shear force along the length of the beam. That means, along the length of the beam, when they are subjected to uniformly distributed load, if we take any cross section, the rate of change of the moment will be the negative of the shear force. So, this is an important information which will be useful as we will go along in the subsequent lesson. Now, here if you note into that, if this particular quantity shear force becomes 0, then the bending moment in that particular region is going to be constant, because m is going to be a constant quantity c. So, if shear force is 0, then bending moment is constant in that particular region. Now, this in fact we can verify readily if we look into a beam. Say for example, we have a beam which is simply supported. Now, since here we do not have any axial force, so we are saying horizontal at this end is 0. So, this is hinged end and this is roller end, and this is subjected to a uniformly distributed load, say of q per unit length, and the length of this beam is L. Now, if we say these two ends are A and B, so reactive forces are RA and RB. Now, we can take moment about B and we can say that RA into L is equals to Q into L by 2, and thereby RA is equals to QL by 2, and sorry, this is RA. Now, since RA plus RB from the vertical equilibrium is equals to Q times L, so RB also is equals to QL by 2. So, the reactive values RA and RB, they are equals to QL by 2. Now, supposing if we like to take the free body of this beam at a particular section which is at a distance of x from this left end, then what we have is this reactive force here over here, which is RA. Then we have uniformly distributed load over this particular portion. We have the shear force, the positive shear force, and the bending moment. So, this is V and this is M. Now, if we, and this is Q per unit length. Now, this distance as we have noted is x. So, if we take the vertical equilibrium of the forces, we have V plus R A minus Q times x, this is equals to 0. This gives us that V is equals to Qx minus Ra, and Ra as we have seen is QL by 2. So, this is equals to Qx minus QL by 2. Now, if we take the derivative of this dV dx, then this is equals to Q, which conforms to the derivation as we have seen right now. Now, if we compute the moment at this particular point, let us remove this. Now, if we compute the value of the bending moment, if we take moment about this particular point, then we have moment m, which is in an anticlockwise direction. Now, moment contribution of Ra, which is in a clockwise direction, is minus Ra times x, and the moment contribution of this downward load also in an anticlockwise direction, which is positive, which is Q times x square by 2. So, this is equals to 0. So, this gives us m as equals to R A into x minus Q x square by 2. Now, if we take the derivative of this, then dm dx, this is equals to R A minus Q x. Now, R A as we have seen is QL by 2. So, this is QL by 2 minus QX, and this is nothing but equals to minus V. V, as we have seen, is equals to QX minus QL by 2. So, dm dx, if we substitute for QL by 2 minus QX as minus V. So, this is the expression which we have obtained, that dm dx is equals to minus V. So, this can be verified from this particular example, that we get dm dx as equals to minus V, and we get dV dx as equals to Q. Now, let us look into that if the beam segment is subjected to a concentrated load. Now, as we have shown earlier, that we have a part of the beam, we take out a small segment, the length of which is dx, and over this dx a concentrated force or a concentrated load is acting on the beam, which is P. Now, here if you note that in the previous case we had the change between V over the length dx as V plus dV, here we have noted as V plus V1. Now, in the previous case we had uniformly distributed load over the small segment, so the variation was comparatively less, but in this particular case we have a concentrated load acting at the on the beam at that particular point, and the change over from the left of the beam to the right of the that concentrated load, from the left to the right, there is a drastic change, and that is why, since there is a finite change, we have designated the right hand shear by a change over a finite value. So, left hand side we have the shear as V, and the right hand side we have V plus V1, V1 being a finite value which can give us the change due to the concentrated load, and so is with the moment M1. Now, if we take the equilibrium of the vertical forces, then what we get is that B plus V1, which is acting in the upward direction, minus V, which is acting in the downward direction, minus P again is acting in the downward direction. So, this is equals to 0. So, this gives us that V1 is equals to P. Now, this particular expression gives us the information that on the right hand side the change in the shear from the left hand support is equivalent to the addition of this concentrated load. So, on the left hand support or the left hand side of the concentrated load, the shear force whatever we get, that gets changed by the quantity of that concentrated load over the right side. So, on that left side we have the shear of V, on the right side we have the shear of V plus P, which we have called as V1. So, V1 in this case is P. Now, if we take the equilibrium of the moments about the left edge of the beam element, then again M plus M1, which is a positive anti-clockwise moment, which we have considered as positive, minus M, which is a clockwise moment which is acting on the left edge, plus the moment due to V plus V1 is V plus V1 times dx, and the contribution in the moment due to P is P times dx by 2, and B does not have any contribution because we are taking moment about this edge, and this is equals to 0. Now, this gives us that moment M1, after cancelling the terms, we get that M1 is equals to P times dx by 2 plus minus V times dx minus V1 times dx. Now, these quantities dx being small, so there is not going to be significant change of moment at the point of the concentrated load between the left hand side of the load and the right hand side of the load. So, if we compute, when we compute the bending moment at different points along the length of the beam, now if we compute the bending moment on the left side of the load and compute the bending moment on the immediately right side of the load, due to the concentrated load there will not be any change in the bending moment. But if we look into the aspect that from the previous expression we have seen that dm dx, the rate of change of the moment, is equals to the negative of the shear force. So, on this side we have V, and on this side we have V plus V1. So, on the left side the value of dm dx is equals to minus V, and the value of dm dx on the right hand side is minus V plus V1. Now, as we have seen, V1 is equals to P, so this is equals to minus V minus P. So, you see there is a drastic change in the value of the rate of change of the moment from the left side of the concentrated load to the right side of the concentrated load. Now, on the left side of the concentrated load, the value of the dm dx whatever we have, on the right side there will be a difference of this minus p over the dm dx value on the left support. So, there will be a drastic change in the rate of change of the moment because of the concentrated load. So, this is an important observation. Now, many a times as we have seen that in a beam we can have a concentrated moment, again considering a small part of the beam which is of width dx, and in this patch we say that at this point there is a concentrated moment m0 which is acting over here. Now, again the positive shear and positive moment is indicated over here, and consequently the negative shear and the negative moment on this face. Now, if we take the equilibrium of vertical forces, then the equilibrium of the vertical forces gives us that V plus V1 minus V is equals to 0, which tells us that V1 is equals to 0. Now, the meaning of this that V1 equals to 0 is that along the length of the beam, if there is a concentrated moment, then there is no change in the shear force. So, along the length of the beam, whenever we come across a concentrated moment at a particular point, and if we are computing the shear force on the left of that concentrated moment and the right of the concentrated moment, we will find that there is no change in the shear force. Now, what happens to the bending moment? Now, if we take the equilibrium of the moments about the left edge of the beam element over here, then again we have this anticlockwise moment m plus m1. Then we have the clockwise moment which is m, plus we have this anticlockwise moment which is m0, and then the moment contribution of this shear V plus V1 times dx, this is equals to 0. Sum of all the moments with respect to this left edge is equals to 0. Now, if we neglect the terms which are multiplied with the small quantity dx, then we can neglect this particular quantity and m gets cancelled with this. So, we are left with that m1 is equals to minus m0. So, this indicates that on the left hand side we had the moment m, on the right hand side of this particular small length dx we have m plus m1, and m is getting added with this value m1, where m1 is minus m0. That means, whatever moment we get on this left edge of the moment, on the right edge this quantity m0 gets subtracted with this value, and finally we get the moment over here. So, at a point wherever we have a concentrated moment, then we find that there is no change in the shear force from the left to the right of that concentrated moment, whereas when we compute the bending moment on the left of the concentrated moment, whatever moment value we get, that again gets modified by the amount the concentrated moment is acting just immediately right of the concentrated moment. So, again this is an important observation which will be necessary when we will be computing the values of the shear force and the bending moment in the length of the member, and that is what we will look into now through the examples. Well, before we go into the evaluation of those quantities, let us look into the previous examples which I had given to you last time. Now, here the first example which we had given to you was the beam ABCD has overhangs at each end and carries a uniform load of intensity Q. So, this intensity Q means it is Q per unit length, and this is uniformly distributed over the entire length. So, the distance between the supports B and C, B is a hinge support and C is a roller support, and the distance between B and C is L. From B we have an overhang of B, from C also we have overhang of B, and this is subjected to uniformly distributed load Q. Now, we will have to find out the ratio B by L, the B by L, so that the bending moment at the midpoint of the beam be 0. So, for what value of B by L, the moment if we call this as a E, moment at E is equals to 0. So, this is the aspect which we will have to look into. Now, before we start this particular problem, if you look into that, this is the overhanging part which is of length B, and since the intensity of the load is Q per unit length, so over this particular width B, the load which will be acting is equals to Q times B. The intensity Q per unit length times B is the total load, and that will be acting at the midway between this distance, which is B by 2. Now, if we like to transform this beam into a beam which is supported on B and C with this effect of these overhangs, then the effect of overhangs will be transfer of this concentrated force over this support. We can transfer this concentrated force over this support, but since at this point we did not have any concentrated force, so in the opposite direction there has to be one force. So, this opposite force along with this forms a couple, and this gives a moment of this nature which is anti-clockwise. And similarly, if we transfer this concentrated force over here at this support, we will have a concentrated force, and then this is going to cause a clockwise moment at this point. So, if we make a reduced form of this particular diagram, it will be something like this, wherein you see that we have the replaced now the hinge support with the reactive forces, which let us call this as RB and let us call this as HB. Let us call this reactive force as RC, and this is being roller. So, it is constrained to move in the vertical direction only, and it can have movement in the horizontal direction, and thereby there will not be reactive force generated in the horizontal direction. So, there will not be any horizontal reactive force at the roller support. Now, you see that the effect of the overhang which we had, that we have now converted in terms of the vertical forces and the moment, and the magnitude of this vertical force is equals to Q times B, and the magnitude of this moment is Q B square by 2. Q B times B by 2 is Q B square by 2, and so is this is Q times B, and this is Q B square by 2. Now, let us find out first the values, reactive values B and C. Now, if we take the moment of all the forces with respect to B, so moment about B is equals to the reactive force RC multiplied by the length L, which is in the anti-clockwise direction. Then we have this moment which is at C, which is in a clockwise direction, minus Q B square by 2. Then we have this moment which is anti-clockwise direction, which is plus Q B square by 2. Then the moment of this particular reactive this force from overhang, which is Q B, and this is going to cause a clockwise moment. So, this is minus, which is Q times B times L, and we have the load, uniformly distributed load, which is again causing a clockwise moment. So, that is minus Q times L by 2. So, this is equals to 0. Now, this part gets cancelled. So, we have RC times L is equals to Q L square by 2 minus or plus Q B L. So, this gives us a value of RC as equals to Q B plus Q L by 2. Now, you can readily evaluate this value of RC from observation also. Now, this reactive force or the value Q B, which is acting at this support point, which is the effect from the overhang, gets transmitted directly to this support, which is Q B, and over a length of L we have uniformly distributed load Q per unit length. So, the total load is Q times L, and this being symmetric, half load goes here, half load comes here. So, which is Q L by 2. So, we get this as the reactive force, which is Q B plus Q L by 2. Likewise, since we do not have any horizontal force, so summation of horizontal force equals to 0 will give us the value of H B as equals to 0. So, value of RB also will be equals to from symmetry as QB plus QL by 2. Now, what we will have to do is we will have to find out the ratio between the length B to the length L in such a way that the load produces 0 bending moment at the mid span. So, if we can compute the magnitude of the bending moment at mid span, and if that we equate to 0, then we can find out the ratio between the B and the L. Let us do that. Now, if we compute the value of the bending moment, so let us keep in mind that RB is equals to QB plus QL by 2 and RC also is equals to QB plus QL by 2. Now, if we calculate the value of the bending moment at E, so moment if we take the free body part of this particular end, say the left end of the beam, here we have the vertical reactive force which is RB, and HB being 0 we are omitting that. Here we have the vertical force which is QB, and we have an anticlockwise moment which is QB square by 2, and we have over this particular part distributed load which is of intensity Q, and this being the mid span, so this length is equals to L by 2, and on this particular cart there will be the stress resultant which is the positive shear which is V, and the bending moment M which is anticlockwise. Now, if we take the moment of all the forces with respect to this particular midpoint, then we can write M which is anticlockwise moment, then RB is going to cause a clockwise moment. So, M minus RB times L by 2, and QB is going to cause again an anticlockwise moment. So, this is plus, so Q times B times L by 2, and the uniformly distributed load also will be causing an anticlockwise moment. So, that is positive. So, that is Q times L by 2 times L by 4, half the distance, and we have this moment which is in an anticlockwise form which is QB square by 2. So, these are the moments which we have, and this is equals to 0. Now, we have seen the value of RB is equals to QB plus QL by 2. So, if we substitute that, then we get the value of M minus RB is QB plus QL by 2 multiplied by L by 2. So, minus QBL by 2 minus QL square by 2, I mean L by 2 and QL by 2. So, QL square by 4 plus QBL by 2 plus QL square by 8 plus QB square by 2, this is equals to 0. Now, from here if you look into this term gets cancelled, and so M is equals to, now QL square by 4 negative and QL square by 8 positive. So, that gives us QL square by 8 negative. So, we get M minus QL square by 8 plus QB square by 2, this is equals to 0, and hence the moment value M is equals to QL square by 8 minus QB square by 2. The value of the moment is equals to QL square by 8 minus QB square by 2, and since the moment criteria is that moment has to be equals to 0. So, we write then QL square by 8 is equals to QB square by 2. So, Q gets cancelled, this is 4. So, we get B square by L square is equals to 1/4, or B by L should be equals to half. Now we take the, I say plus minus, so we take the plus value because minus half has no meaning in this sense. So B by L is equals to half. If we maintain this particular ratio, then the beam which we have seen where this is hinged and this is on roller with overhang of quantity B with uniformly distributed load will produce a zero bending moment over here. So, but then the value of this particular part has to be equals to the half of this length. If this is L, this has to be L by 2. So, if you have this distribution, then the moment at this particular point will be equals to 0. Well, the second example which was set last time was that determine the shear force and bending moment at D, which is 2 meter from A. Now, this distance between A and B is 4 meter. Now, what you need to do is that at a distance of 2 meter, we will have to find out the values of shear force and bending moment. Now, if we look into here, that we have a load of 4 kilonewton which is acting at a distance of 1 meter, vertically 1 meter above this particular support point. Now, here of course, we neglect the this weight and we take up to the center of the beam as the transfer of this. Now, this particular force can be transferred at the center of this beam. Now, if we do that, then since here we did not have any force, we will have to have an opposite force. So, this force along with this forms a couple which is anticlockwise in nature, and the magnitude of this moment will be equals to 4 times 1, which is 4 kilonewton meter. So, the effect of this particular 4 kilonewton force which is acting at a distance of 1 meter from support A is equivalent to a 4 kilonewton load at this particular point along with a moment of 4 kilonewton meter. So, now that if we transform this beam with this particular change, that means we take this effect of this load in terms of the load and the moment and remove the supports to have the reactive forces, like at the hinged end you will have the vertical and the horizontal force, and at the roller end you will have the vertical force. So, if we take the free body of the whole beam, then we can find out the values of the reactive forces and thereby we can compute the shear force and the bending moment. So, if we take the free body of the whole beam, this looks like this, that the 4 kilonewton load which was acting at a distance of 1 meter from this support is now transformed to this place where we have a horizontal force of magnitude 4 kilonewton and the moment is 4 kilonewton meter, because 4 times 1 will give you 4 kilonewton meter as the moment. Now, the reactive forces which are acting at A and B, they are RA, let us call this as HA, this as RB, and there is an overhang of 1 meter from B. Now, all we will have to do is first, because we need to evaluate the bending moment and shear force at this particular point D, which is at a distance of 2 meter from left end. Now, let us compute the values of the reactive forces RA and RB. Now, as we know the equilibrium of the forces, summation of horizontal forces equals to 0. Now, here the assumed directions as we have, that HA is in the positive x direction minus 4 kilonewton axial force which is acting is equals to 0. So, HA is equals to 4 kilonewton. Now, if we take the moment of the forces with respect to this point B, then what we have is, now since 4 kilonewton and HA they are acting in the axial direction, they do not contribute to any moment. When we say about the point B, means we take with respect to the center of this beam. So, the moment contribution of RA is RA times 4, which is a clockwise moment. Now, if we have called this as positive, then we have anti-clockwise moment which is 4 kilonewton meter, which is minus 4, and then we have 8 kilonewton load which is causing a moment over here, which is again a clockwise moment. So, plus 8 into 1, So, this is the total moment contribution of all the forces, and this is equals to 0. So, summation of moment at B, we have taken this as equals to 0. Now, this gives us that A into 4 minus 4 plus 8. So, this is plus 4, this is equals to minus 1 kilonewton. So, the value of the reactive force at A is equals to minus 1 kilonewton. Now, if we take the other equilibrium, which is summation of vertical force is 0, then we have R A plus R B is equals to only vertical force which we have is 8 kilonewton is equals to 8. Now, R A we have obtained as minus 1. So, R B is equals to 8 minus R A, which is minus 1. So, this is equals to 9 kilonewton. So, the reactive forces which we have is R A equals to minus 1 and R B is equals to 9 kilonewton. Now, if we calculate the bending moment at this point D, let us take the free body diagram of this particular part from the left hand support and substitute all these forces, so that we can evaluate the shear force and the bending moment. Now, if we take the left part, then what we have is, this is the left part of the beam up to point D. Now, on the right hand side, the positive shear is V, the bending moment positive is M. Now, here we have the reactive force, which is R A, and here we have the 4 kilonewton force and the bending moment 4 kilonewton meter. Now, if we take the vertical equilibrium of the forces, that means summation of vertical forces is equals to 0, which will give us the value of the shear. So, V, which is positive upwards, minus R A, this is equals to 0. Now, R A we have obtained as minus 1. So, V is equals to minus 1.0 kilonewton. So, this is the shear force at this particular point. Now, if we take moment of all the forces with respect to this particular point at the midpoint, which is D. So, moment at D, which is anticlockwise, then the contribution of the reactive forces R A, again it is in a clockwise. So, minus R A times the distance, which is 2 meters from point A, and we have this moment 4 kilonewton meter, which is again in anticlockwise. So, it is in line with M D. So, this is positive 4 kilonewton meter. So, this is equals to 0. Now, the value of R A we have obtained as minus 1. So, this is moment at D. So, minus 1 times 2 to the plus 2 plus 4, this is equals to 0. So, moment at D is equals to minus 6 kilonewton meter. Now, interestingly, if you look into the values of the shear force and the bending moment as we have obtained at this particular point, shows us that V is equals to negative 1 kilonewton and moment as minus 6 kilonewton meter. Now, this indicates that the direction of the shear force, as we have assumed at this particular cross section, is on the opposite direction, and hence the values, the magnitude of the shear at this particular point is 1 kilonewton and magnitude of the bending moment at this point is 6 kilonewton meter. Well, let us look into another example problem. Now, here the load is varying linearly, but as we had seen earlier, it is in the form of a trapezium, that here we have 30 kilonewton per meter as the load, and here we have a load of 50 kilonewton per meter, and the length of the beam is 3 meters. So, this is point A, which is hinged, and as you know, at the hinged point we will have vertical reaction and the horizontal reaction, and this is a roller end wherein we will have the vertical reaction only. Now, what you need to do is that calculate the support reactions, shear force and bending moment at midpoint of the beam. So, you will have to find out the values of R A, H A, R B, and we will have to compute the value of the bending moment, which is at the center of this beam, which is at a distance of 1.5 meter from the left support or from the right support. Now, let us look into the free body diagram of this particular beam. Now, this is the free body diagram wherein let us call this particular reactive force as R A, let us call this as H A and this reactive force as R B, and the intensity of the load at this point is 30 kilonewton per meter. The intensity of the load here is 50 kilonewton per meter. Now, if we try to find out the bending moment and shear force at the midpoint, first let us find out the reactive forces R A, R B, H A. Now, if we take the equilibrium of the forces, summation of horizontal forces equals to 0, this gives us that H A is equals to 0, as there are no horizontal forces acting in the beam. So, the values of H A is equals to 0. Now, if we take the moment of all the forces with respect to say point A, then we can compute the reactive force R B. So, R B times 3 is the moment with respect to A, which is in an anti-clockwise direction. So, let us give the notation that is in the anti-clockwise direction. Then H A R A obviously will not have any contribution, since we are taking moment at this particular point. Now, the load part, the trapezoidal load, we can distribute in two parts. Let us call that this is of uniform intensity, and this being 30 kilonewton per meter, we have this as 20 kilonewton per meter. So, we have two parts, one is the rectangular part which is 30 kilonewton, and another one is a triangular one from 0 to 20 kilonewton per meter is varying. Now, this load, if we take the moment of all these uniformly distributed load over here, they are causing a clockwise moment. So, this is negative. So, minus of 30 into 3 into 1.5 is the contribution due to the uniformly distributed, which is 30 kilonewton per meter. So, 30 into 3 times 3 by 2, which is 1.5, minus half into 20 into 3 is the triangular load, which is acting at a distance of 1/3 from here. So, the moment is 1/3 into 3. So, this is equals to 0. Now, this moment also is a clockwise moment, and this moment also is a clockwise moment, and that is why they are negative. So, R B into 3 minus this gives us a value of 135 minus 135 minus, now this gets cancelled and this is 30. So, from here we get a value of R B, which is equals to 165 by 3 is equals to 55 kilonewton. So, if we take the vertical equilibrium, which is R A plus R B equals to the load, and the total load which is acting in this particular case, if we take the vertical equilibrium of the loads, so R A plus R B is equals to half 30 plus 50 times 3. So, this is 40 times 3, which is 120 kilonewton. This is the total vertical load that is acting on this particular beam, and R B being 55 kilonewton, R A is equals to 120 minus 55, which is equals to 65 kilonewton. So, these are the reactive values of this beam. R B is 55 kilonewton, R A is 65 kilonewton, and the value of H A is equals to 0. Now, if you compute the bending moment and shear force at this particular midpoint, then let us take the free body of that particular part, so that you can evaluate the value of the bending moment and the shear force readily. Now, here we have this particular beam, which is of distance 1.5 meter, because this is the at the midpoint we have the R A over here, and here we have the trapezoidal variation. Now, if you compute the value here, it comes as 40 kilonewton per meter, and this is 50 kilonewton per meter. and the positive shear is in this direction, positive bending is in this form. So, this is V and M. Now, if you compute the value of shear, so V plus R A minus half of 40 plus 50 into 1.5, this is the total load, this is equals to 0. So, V is equals to, as we have seen, the value of R A is equals to 65 kilonewton. So, this is minus 65 plus this is 45 times 1.5, which is 67.5. So, this is equals to 2.5 kilonewton. And if we compute the bending moment, if we take the moment of all the forces with respect to this, you will get moment of these forces with respect to, either we can take moment with respect to this or with respect to this with of all the forces, and the moment comes as equals to 45 kilonewton meter. So, at the mid span, because of this trapezoidally distributed load, you have the shear force as equals to 2.5 kilonewton and moment is equals to 45 kilonewton meter, and both are being positive. So, the directions assumed in the cross section there the right. Well, we have another example problem where a simply supported beam is loaded as shown. Determine the shear force and bending moment at cross section A and BB. Now, these cross sections A and BB which are shown, they are not any fixed point, but we can assume that they are at a distance of x from A, and this also we can call as a distance x from A. Now, the idea behind this is that we can find out that what is the effect of this concentrated moment, or what is the effect of this uniformly distributed load which is up to a distance of 5 meter, and beyond 5 meter what happens to the shear force and the bending moment. Now, if we compute the values again in the same form, after computing the reactive values, we can write in a general form as the values of shear force and bending moment at the section A and section BB, and we can write down the values of V and M as a function of x. Now, this I leave on to you, go through this particular problem, try to evaluate the values at A and BB. We will discuss this problem in the next lesson. Well, then to summarize, in this particular lesson we have included the recapitulation of the previous lesson part. We have looked into what aspects we discussed last time, then the relationship of different types of loads with shear force and bending moment. Now, as we have seen that how the shear force and bending moment gets related to the uniformly distributed load, the concentrated load, and if you have a concentrated bending moment at any point along the length of the beam. And then we have looked into some examples to evaluate reactive forces, shear force and bending moment for different types of loading. Now, some questions are set for you, which is for a uniform loading on a portion of a beam, what will be the variation of shear force, and what is the effect on bending moment if shear force on a portion of a beam is 0, and what is the effect of concentrated load at a point in a beam on bending moment at that point. Now, we will give you the answers in the next lesson. You can go through the lesson and look for the answers of these questions. Thank you. Welcome to the third lesson of the fifth module, which is on bending of beams part 3. In fact, in the last two modules or in the last two lessons, we have discussed some aspects of the bending of beams. We have looked into the concept of shear force and the bending moment. Now, in this particular lesson, we will see that how to evaluate the variation of shear force and bending moment along the length of the beam, and the related aspects will be discussed in this particular lesson. Well, once this particular lesson is completed, it is expected that one should be able to understand the concept of shear force and bending moment diagrams. Now, as we have seen so long that we have calculated the shear force and the bending moment in a beam at a particular location along the length of the beam. Now, if we like to find out that how the shear force is valued